All right. So CVE 2018-1160. A lot of you guys have been messaging me about this, which, hey, I love to see the excitement for exploit development. I really do. All right. And I'm going to keep pushing these out. I shouldn't say that because who knows? but, uh, but yeah, in all reality, if you guys get this, if you guys get a shell, if this is your first CVE, please comment down below. If it is your first CVE, hey, honored that you're going to be doing it with me. All right. That's pretty sick. But regardless, tweet me on Twitter if you do get a shell, send me a picture, and then I'll retweet it, et cetera, et cetera. I think it's gonna be badass. Now, if I see the exact same exploit code like I'm seeing like back here, all right, come on, guys. like don't do me like that, okay? Don't do me because if you guys are copying and pasting my exploit code, I'm gonna post the one that doesn't have like the completed brute force thing. It'll make sense towards the end, all right? You guys are gonna get everything you need to beat this challenge. I'm gonna teach you. You will get a shell by the end of this if you follow along. But that said, I expect to see different pieces of code if you guys complete this challenge. If I see my code over and over and over again, diabolical, guys. Don't do me like that, all right? But all right, let's go ahead and get started. And again, actually, before we get started, I'm memeing. I'm laughing my ass off over here over this because believe me, I look scuffed because I've been editing and whatever. The point is this. All right, this is an intermediate, I would say borderline difficult exploit. So don't get frustrated if you don't get it right away. Just keep trying. All right, it'll eventually stick and it will be worth it. I promise. Okay. Nothing that's easy is ever going to be worth it. If it's easy, it's probably lame, right? But if you work towards it, you're going to be happy with the end result. Anyway, all right, I'm going to quit yapping. Let's jump in. Whenever we pull up the challenge, we're given access to the kernel version that the target is currently running. And of course, we're given a hint that the kernel version may have changed since the environment is being updated. Now, in addition to this, we also get the source code files and a libc file. So the libc file would be more important whenever we're creating our gadgets, but we can go ahead and ignore this for now. And the target environment that I actually decided to use to emulate this is going to be Ubuntu 16.04.7 LTS. Now, I recommend you download this version just to follow along with me, since during the vulnerability analysis, this is an open source application. So we will be following along the debugging session with source code enabled. This is an incredibly powerful feature of the GDB debugger, and I don't see many people using it. So what better way to learn than through a challenge like this? So even though I do have my target environment set up, you more than likely have just installed Ubuntu. So before you get started, make sure you've installed these particular packages. You don't necessarily need Vim, for example, or even OpenSSH. So if you want to debug locally, you can do so. But since we're dealing with a remote protocol, I recommend you do what I do, which is remote debugging. That said, let's go ahead and enter the workspace directory. This is basically something I created. And within it, you can see that I actually do have all the binaries installed that were obtained from pwnable.tw. I recommend you do the same, and we're going to go ahead and clone the actual open source repository. When we're dealing with an open source application for research or exploit development, if you have access to source code, why wouldn't you use it, right? So let's go ahead and clone it. I'm renaming it as Netatalk.source just so I don't get it confused with the pwnable binaries. And so we can see it downloaded there. We're going to go ahead and enter that directory. And we're going to log, or rather grep using git log for CVE TAC 2018 TAC 1160. This is the CVE we're going to be analyzing. And so, of course, we're given a couple commit hashes, but I know for a fact this is the commit hash that includes the patch. And if we continue scrolling down, we can see that there's another commit hash just before it. So I'm going to go ahead and select this one because I'm making the assumption that because the patch one is above it, this is more than likely going to contain the vulnerable implementation. So I'm going to copy that. And I'm going to do a git checkout and then the actual hash that we just copied. So we're going to get this error. This is completely fine. But to be sure that we actually did get into that particular source code, we're going to do git rev parse and then head. Nice. So at this point, we're pretty much ready to compile. So the first thing we're going to want to do is actually run Bootstrap. This is basically going to prepare the configurations needed to detect our environment. So let's do Bootstrap. All right, next we're going to actually run configure. And so this is basically gonna choose the appropriate compiler settings. Hopefully it doesn't click enter here, and it did. But basically, before I run it, I want to go over all the command flags that we're going to be running alongside the configure script. So the C flags and the CXX flags. What does this mean? Basically, C flags are the flags that are going to be used by C files. CXX is C++ files. So these are the flags to use when compiling those files. Now, the TAC-G3 used by both of them is basically saying we want the maximum debugging symbols available to us. TAC-O0 is basically disabling any optimizations. This is great for when we're doing debugging. And TAC-F no omit frame pointer is pretty much the same thing in the sense that we're removing additional features that would normally be included during compilation because we ultimately just want to see the flow of things, right? And lastly, we pass TAC enable large file to configure in case the output is larger than 2 gigabytes. It's always good to just do this just to get out of the way. So let's go ahead and run this. Nice. So if you got this screen, everything's good. Basically means that we had success in running the configure script. Now we're actually ready to perform the actual compilation. So to do so, we're just going to type make. Nice. So at this point, everything should be good. We should have successfully compiled AFPD. And now we're going to actually test it. First thing we want to do is actually make sure that our environment is set up properly. I've already made a workspace directory, so of course, if you don't have it, you're going to have to create it yourself. And then we're going to do scp tac-r, the username that we provisioned the target machine with, the host name, and then I have uploaded my SSH key, so of course I have autocomplete to be able to give it the path as I'm doing so now. But in your case, if you haven't done so, you're going to basically have to enter the password and know this path by memory. In my case, it's /home/me workspace, a star to indicate we want all of the contents from within the directory, and then a period to indicate we're downloading it to our current working directory. So let's go ahead and let that run. All right, with everything downloaded, we want to go ahead and install the client. Now I've already done so, but in the event that you haven't, you're going to do sudo apt install meta talk tac tools tac-y. And of course, since I have it installed, I'm not even going to get an update since it's already the newest version. And we can now actually go ahead and SSH back into the target environment because we're going to run the binary now. Because at this point, we should have everything we need to actually confirm that we've set up the path and everything properly. So with that, we're going to go into the actual compiled version, not the one that we downloaded from Pwnable. So workspace, node attack source, etc afpd, and here we can see the afpd binary. So let's go ahead and run it. afpd tac-d to daemonize, tac-f to read a config file, and here we're not gonna use one that's provided with the source code. Instead, we're gonna use the one from pwnable.tw. Now, I know it seems weird because we're using our compiled binary and not the target environment's binary, but because we're kind of just trying to see the natural flow of things with source code, we still want to emulate it as closely as possible despite not using the same binary. So we're going to basically give it that config, which is workspace, netatalk, then I believe it's afp.conf. And I'm going to do an ampersand just so I get the PID returned back to me. And so if we do ps tac aux and we grep for afpd, we'll actually see that the binary isn't running as afpd, it's running as lt tac afpd. And this is important just because I like to use PID of. It's basically a command that allows you to get the process ID of a binary if you know the name. So we're going to do sudo gdb server, and we're going to listen on 1, 2, 3, 4, and we're going to attach to the PID of lt tac afpd. Nice. So at this point, we can go back into our Kali machine, enter the workspace directory, and we're going to basically do the same thing that we did on the remote machine. We're going to go to our source code version. So netatalk tac source, etc afpd, and we're going to do pwn dbg afpd. And we still need to connect to the remote host. So we're going to do target, remote, challenge, and we know it's listening on 1, 2, 3, 4. So it'll go ahead and read the symbols from the target. And even though we are able to now perform debugging, as I mentioned before, we want source code as we step through this. So we're going to do set substitute path, and we're going to do /home meme, and then workspace, and Metatalk tac source. And we're going to do the same thing, except we're going to change the username to our username. In my case, it's wetwork, and workspace Metatalk tac source. So assuming that these paths exist, we should now be able to see source code when we hit our breakpoint. And we're going to set a breakpoint at DSI get session. And the reason we choose this function is because it's one of those functions that's going to get hit every time a client tries to connect to the server, right? So let's go ahead and hit C. And we'll open a new session here. And we're going to do AFP login test, the host, which is going to be challenge. And then we're going to set the port as 556 or 5566 because that was what was in our config file, right? So it's going to hang there. But if we go back to our actual pwnable session, we can see that we now see where in the source code we actually are, in addition to the disassembly, which is in the upper window, which I'm going to make the font smaller just so you can see the entire thing. So of course, registers, disassembly, source code, stack, and then of course the call stack. So with that, we know that we have successfully set up debugging symbols, debugging source, whatever you want to call it. So if we hit continue, it'll go ahead and exit. And we can see that we did, in fact, pass the open session, or rather guest login failed, et cetera, et cetera, et cetera. So now we can actually proceed with the analysis of the vulnerability. So I'm going to go ahead and close all these out. And let's actually pull up the CVE. All right, so taking a look at this GitHub page, which you can find it by basically Googling the CVE GitHub, and it'll take you to this page. And it gives us a rundown of how the vulnerability occurs. So it tells us everything we need to know to begin crafting our proof of concept. But I'm going to give you a quick rundown of what I've observed. So basically, it occurs due to a mem copy, right? And all three of the arguments that are passed into this function utilize the DSI structure. This can be seen here. And different members are used within different parameters. So in this case, our amount of data that's going to be written is controlled by the command's member, the first index, right? Or rather, whatever I is at that moment. And then DSI tac commands plus I plus 1 is what's going to be used as the source, rather where data is going to be coming from to be written to ATT and quantum. So basically, if we can define this as a large quantity, we can overflow any members or data that begins from this address. So let's open up a terminal and let's actually look at dsi.h, which contains the definition for the structure. So I'm going to do a little bit of bash foo vim, and then I'm going to do find dot tac name dsi.h. And so this pulls up, of course, the header file. I'm going to make it a little bit smaller just so you get a better overview of everything that we're seeing here. It does give us a rundown of what a packet looks like. Now, I won't be going over the reverse engineering of the DSI packets or the Apple file protocol or AFP, which I'm going to refer to it now going forward. I think that's a good exercise for you. With the last videos that we've done, you should have a firm understanding of how different variables and structures are laid out, so you can do that. It might take you a little bit longer, but keep in mind, practice makes perfect. And at the end of the day, if we go through the reverse engineering process through all of these, it's going to take a considerable amount of time. So going down, we can see starting on line 60, we get the definition or the type def for the DSI structure, which, just to point it out, it's here. And the corruption begins on line 75 here. Now, based on what we see here, the commands pointer rather is of type uint8t. Now that means that this is a 1 byte pointer. So anything that this pointer is pointing to, it's going to treat it as a byte, which means that the source, or rather the length that we're going to be using for the mem copy, is limited to 1 byte. Now the largest byte you can have in terms of a decimal representation is 255, so 0xFF. Which means if we start corrupting here at line 75, yes, we can corrupt the commands pointer, but we more than likely cannot completely corrupt the data array. And in fact, we know this to be true here because on line 56, we see that it's defined as 65,536. So we could only overwrite parts of the data buffer. And we can see that, of course, that's going to be the DSI reply buffer. Now, the DSI receive buffer is what's pointed to by the commands pointer. So theoretically, even if we didn't read this and we're just kind of observing and looking through the source code, we can kind of assume that if we were to corrupt the commands pointer, anything we send to the AFP server is going to be written by whatever's pointed to by the commands pointer. And in fact, if we continue to read through the documentation, we would see that basically whenever we do this, and let me see, all subsequent AFP packets will be written to that location if we overwrite the commands pointer. And it does seem to be a heap allocated pointer. And so this kind of gives us a solid idea of how to approach this vulnerability. So let's go ahead and actually start looking at some other source code files. In this case, we're going to look at dsi opensesh.c. And the reason we're going to do dsi opensesh.c is because if we were to scroll down, of course, we're told the file where this vulnerability occurs. So let's go ahead and open that one up. And if we scroll down here, we can see the memcpy occurring here. Now, in order to reach this condition, we have to trigger this case from the switch operation on line 34. So again, I'm not going to be going over the reverse engineering process this time, but basically, this is part of the way that the protocol is going to be sent. So I'm going to actually put this one to the left here and open a new terminal. And we're going to go into the Python code directory where I have the first POC. And so basically, we're going to be able to enter this because we're sending it here as part of the DSI open session command. So 0x01. Now, that said, let's go ahead and break down this proof of concept function by function. Let's go to the very bottom just to make things easier. So first we have the create socket function, right? So this is basically just creating a TCP socket. This is what we're going to be able to use to communicate with the protocol because of course it is TCP based. Next, I've created an unpack DSI packet function. Now this is basically what I use to understand the protocol because again, whenever you're reverse engineering, these are the types of things you create to understand the protocol because at the end of the day, if you don't know how to communicate with the server, you're going to have a lot of trouble during the exploitation or even just the research side of things. So, which shout out to this author here. Let me see if I have the link. Here it is, Jacob Baines. So he's actually the person who discovered this vulnerability. He has an entire blog post where he goes over this, which this POC that we're going to be looking at here, it's very similar to what he does in his blog post. So I heavily recommend that you go ahead and read this. But what I was saying is, yeah, the way he does it and the way that he's looking at the protocol, you can tell that he spent time understanding the protocol before he even got to the phase where he's looking for bugs, right? At least that's my assumption. I could be completely wrong and he's a genius and he just knew AFP, but I'm going to go ahead and assume that he took his time learning the protocol. And he probably had no expectation of a bug. He was just kind of like, I need to understand how it works. I guess that's my perspective. I think whenever you're O-Day hunting, you should kind of go in with the expectation that you're cool not finding a bug. It's more about strengthening that muscle, I guess. Let me go ahead and put this up here. So that said, that's what that function is. The next function we have is the generate DSI function here on line 72. So once again, this is based off the reverse engineering aspect of doing vulnerability research, where I was able to understand how the packets need to be laid out. And of course, since the packets are going to be different every time, depending on what flags and commands we're using, I decided to make a function so that I don't have to, have this by memory. I can just basically plug in the inputs needed to generate the packet and then generate it, right? And finally, I do believe this is the last function. Yes, we have POC. So what this is going to do, which again, shout out to, I keep forgetting his name, Jacob. Okay, shout out to Jacob. I'm probably thinking of the James server, but anyway, okay. But basically what this is going to do is very similar to its write-up. What we're going to do is we're going to overwrite the server quantum member of the DSI structure. Now, if you recall, in fact, we'll pull it up again. You can see that this is here. So we're going to first overwrite, of course, the ATTN quantum, the data size, and the server quantum. And this can be seen in the proof of concept as well. So we're overwriting the data size, the quantum, and then finally the server quantum. Now, the reason why we're putting deadbeef in the server quantum, which you'll see here soon, is because we're actually going to get this reflected back at us. So this is a cool way to see it per se, like dynamically from our point of view, so that we know it worked. But of course, we're going to go ahead and start debugging. So let me go ahead and close this window here. Make this a little larger. And I've actually already went ahead and created a GDB script to do this. So I'm going to do cat GDB scripts, trigger source. And basically, I'm going to connect to the target environment. I'm going to set up the source code path, and I'm going to break on DSI open session. So let me go ahead and open a TMUX session, and I'm going to SSH into the target environment so that I can launch the actual binary. Because of course, we're at the point now we're going to be doing the dynamic testing. And so I'm going to do pwn. Oh, getting ahead of my head self. So I'm going to enter the workspace directory, enter the netatalk source, etc afpd, and I'm going to go ahead and launch afpd, tag D to daemonize, tag F, and read the config for the actual pwnable challenge, which is afp.conf, and then ampersand, just so that it does run in the background. I'm just going to go up because I don't remember the command, but basically what I was doing to debug this, you'll find that because it spawns so many child processes, it's kind of hard to just attach to the first one. So I just do a for loop like this. It's basically going to iterate over every single PID it finds for LT, TAC, AFPD, and then attach, of course. So at that point, we're ready to go ahead and open a new session, do pwn dbg, and we're going to read that GDB script, which is trigger source. And so at this point, it's going to go ahead and attach, of course, and we're going to do continue. And actually, just to cover it real quick so we're familiar with it, but basically, whenever I was debugging this, right, because we're going over this together, so just to be clear, it was not as smooth as it's going to be throughout this debugging process. Whenever I did this myself, I was pulling my hair out, like crying, you know, like the whole shebang. And I found that I had to basically jump between different processes. And in Linux, an inferior, at least from my understanding, I could be wrong, is like a child process in Linux. So you could do info inferiors, and this will give you a list of the different inferiors, or rather child processes that you can attach to. And sometimes you'll get an error where it says something like, you know, inferior X process whatever exited normally. So if that happens, more than likely GDB followed the forked process or the child process, and you have to go back to the parent process. So in this case, if I did info inferiors and that did happen, I would have two processes. And to switch back to the parent, I would have done inferior and then one, right? And then that would have switched me back. But of course, in this case, since we're still in the parent process, we don't have to worry about that. So I'm going to go ahead and continue. And let's go ahead and open the POC. So, or rather run it. So let's go to Python code, Python 3, POC 1, and we're going to do challenge 5566. So there we go. We can see that it's sending it, and of course it broke on the actual debugging side. So if we do a list, we can actually see where the memcpy is here, which makes it easier, of course, because we have source. So I'm going to break on line 36, and I'm going to do C. And so here we can see we're right at when we're going to actually perform the memcpy operation. So I'm going to also do a breakpoint on line 37 because we're going to check the value of the server quantum before and after. So if we do a printf and we do %d because we want a decimal representation, and we do DSI commands, and then we do 0, right? or rather I, which is of course what the loop is currently doing. We see that we get 12, right? Now, if we go back to the POC, cvim POC1, we can see here on the POC function that this is the amount used by the commands I here on line 41. And we know this because it's being packed into a byte on line 43. And just to further confirm this, let's do a Python 3 prompt. Let's import C types. And we're going to do all of these. We're going to add all these up just so you guys can see. All right. I feel like I messed it up. Okay, it did work. So there you can see that it's 12, of course. So we do in fact control the command's I pointer in this case, or rather indexing into that address. And so let's go ahead and also print the server quantum. So let's do hexadecimal this time. And we're going to do server quantum. So we can see it currently holds, what is that, like 100K? So it holds 100K. And we can see here that we've already set the breakpoint on line 37. So let's go ahead and continue, and then let's check it. So we can see we have successfully corrupted the structure, and proof of that being that server quantum now contains dead beef. So let's go ahead and continue. And if we check the proof of concept window, we can see that dead beef was in fact reflected back at us. So at this point, we can go ahead and say, or rather confirm, that we do have a memory corruption. Because I highly doubt that the developers intended for you to be able to corrupt other members of the structure. And because we have a complete, or rather we have complete control over a byte, we technically can overwrite the command's pointer and trigger that condition which we saw in the write-up. So at this point, I'm going to go ahead and look at the second proof of concept code. All right, so we're going to go ahead and do the same approach. We're going to do bottom up, but we're going to skip the functions we've already gone over. So for example, generate DSI packet. We've already covered it in the last proof of concept. The new function we see here is the overwrite commands pointer, which is pretty much the POC function with a couple of additions, right? So for example, on line 100, we see where we actually overwrite the commands pointer. And of course, the first byte that we're using in the DSI open session, or rather the second one, because the first one is the attention quantum, but the second byte is the size that's used by the command's index, or the command's I. And we've added an additional 8 bytes so that we are able to overwrite the commands pointer. And of course, we send it, and then we return true, assuming that everything went well, right? Assuming we get a response back from the server. And now we have a write data function. Now, the reason I created this function was because ultimately this is an arbitrary write vulnerability. I could be wrong about that. It could be a different type of vulnerability, arguably. I don't know what other name you'd give it, but to me, it's an arbitrary write. And so we're basically going to be overriding the commands pointer using the previous function. And then we're going to generate another type of AFP packet or DSI packet. And then we're going to send it. And that should, in theory, write data to that particular location where the commands pointer is now pointing. And then lastly, we close the connection using the DSI func close packet. And if we go to main, we can see that we are in fact doing this. It's writing data using the socket file descriptor that we create with the create socket function. The address that we're choosing here is hard coded, and then the string, the cake is a lie, right? And we do 0x0 because the protocol requires the request IDs to be incremented every time a request is sent. At least that's my understanding of it. And so just to follow the protocol procedure, we're going to go ahead and do that. Now, I'm going to go ahead and get it ready on the left-hand side here. And I'm going to kill the LT tac AFPD just so that I can have a fresh start. So let's do FPD here, and let's do that for loop so we can attach to it. And let's connect using pwnable.tw. Now, you saw that we were using a hard-coded address. Now, I think I can do it from pwnable, but if we do a check sec, we can see that, oh, okay, I guess this one doesn't have pi. So because we compiled it and we removed a lot of the normal features that would be used by this binary whenever it's compiled normally, we're not going to have some memory protections. But we do need to keep in mind that the actual binary does have memory protections, which I should have checksec installed on my Kali machine. If I don't, I'll just SSH into the machine again. But if we do a checksec on the target binary, which is the one we're actually wanting to exploit to be able to capture the flag, if we do checksec, we can see that it has all memory protections enabled. So what does that mean for us? That means that the address is more than likely to change. We can't rely on a hard-coded address to perform our write operations to actually exploit this. So if we do a VM map, we're going to get a random address here. So let's do this one, the last anon. And let's see what's there. So let's do xg, and let's just do 10, or rather 10xg. And we can see that it's, a bunch of nulls and random data, right? So let's continue. And again, we're going to copy this address and we're going to place it into our proof of concept. And save it. And let's go ahead and run it. And it's going to hang there. That's just because we hit our breakpoint. Let's go ahead and hit continue. And if we go back, we can see that it finished completing its operation. Let's hit Control C. That'll drop us into a break. And if we go ahead and dump from that address range again, we can see that there's new data here. And if we dump it as a string, we can actually see that we were successfully able to write data to the location pointed to by the commands pointer. So at this point in the exploitation process, we're ready to begin the exploitation phase. We're ready to see how we can leverage this to get code execution. Unfortunately, because we're dealing with full memory protection, we still have to get a leak, a memory leak. And so now, even though we do have this, without knowing where we're able to write to, because the addresses are going to change each boot, we really have no choice but to look for a leak. All right, so now we're going to be looking at the next proof of concept. I'll be completely honest and transparent here, and in fact, on all the videos, but I had a lot of trouble getting this leak to work, okay? In fact, I was going down a rabbit hole whenever I first approached this. I actually learned a ton about the protocol. I was trying to see if maybe I can corrupt other parts of the structure. And then that way, whenever I invoked a certain request, the data returned to me would be a leak. Now, of course, that's an ideal situation, but that's not always the case. And this is where, like, if you ever had a conversation with me, maybe you met me at DEF CON, Black Hat, or you know me, you know that I'm not opposed to cheating. And what do I mean by that? I think cheating is whenever you seek an answer to get an end result, like you pass an exam, right? So if you're trying to get the answers to pass an exam, you're a cheater. But if you ask for help or you're looking for resources that kind of guide you to understand knowledge that you want to acquire, that's not cheating, right? You're trying to learn. And so there's a difference between getting the answer and learning. So for example, if you're going through this video with me and you're really making an effort to do it on your own before you get to the next step, I think you're going about it the right way. But if you're just waiting for me to release these videos or whatever the case may be, and you just want to get the flag, you have the wrong mindset, right? Because you may go into an interview and you may have a really good CTF score, etc. But when you get through the interview process, you're probably not going to have a good time just because, of course, that's going to be the real test of you knowing what it is you should know, right? And of course, there's times that you're not going to know things. That's completely fair too. This is such a huge field. I have a lot to learn myself. But that being said, I came across a blog post by Taco Pone, or his actual alias may be Jowsy. I hope I said that right. And he kind of goes over how he approached it. I didn't do everything he did, but the initial leak here that we're going to use, I feel like I used his theoretical approach, right? So let's go ahead and look at the next proof of concept. So POC 3. So looking at this, right, we have a new function, the leak address. Now, what this is basically going to do is it's going to leak 1 byte at a time. So how does this work? Because the command pointer is 8 bytes. If we overwrite 1 byte at a time, if we have a valid address, we get a response back from the server. If we have an invalid address, we get no response. Now, this is something that you would have observed testing, of course. I think I kind of got frustrated because I was going down a different path. And so when I saw this, I was like, bro, why didn't I try this? You know, regardless, I didn't use his code. I had to figure out how to get it to work. And in fact, you can see here that depending on the Indianness, etc., that's how I had to format my address when leaking. And I think I actually have an example. I guess I don't here in this function, but continue scrolling down, right? I also made a change to my overwrite commands pointer. So because I'm going to be doing 1 byte at a time, I'm not going to format it as a 8-byte address and then append the offset to get that overwrite to occur. Instead, I'm just going to append the data so that I do 1 byte at a time. And in order to get a good visual of this, I'm going to be printing the bytes as red. So let's go ahead and run this. Let me go ahead and actually launch the server here, which, yes, that's the right command. And I'm going to go ahead and also attach. And I'm attaching specifically just so we can see how this works, right? We're not going to be checking the responses, but we're going to be seeing exactly how it is that we know it's a valid address. So let's go ahead and hit continue. And let's run the POC. POC 3 challenge, and the port is 5566. So there it goes. We hit our breakpoint, and I'm going to go ahead and break on 36 and 37, just because that's when the mem copy occurs, and then of course after it occurs. So I'm going to hit continue, and I'm going to go ahead and print the address of the DSI commands pointer, which is here. So if we do a v prompt, we see this is a valid address, and of course, those are the memory permissions. Now, if we continue and we check it again, we can see that we've overwritten the last byte as a null byte. So if we go ahead and check that, we can see it's still a valid address. So let's go ahead and allow this to continue and go back to the proof of concept. So we can see there that it's pretty much just, of course, trying every possibility. And once a byte is found, it's going to be highlighted in red. So for example, 0 was a valid byte, it was highlighted in red. And now if we go back, technically it's now testing this byte here. Once found, it's going to test this one, then this one, and so forth. So let's go ahead and go back. We see we found another one, EO. And let's go ahead and let this run. And once it finishes, we're going to go back to the debugger. All right, so it successfully leaked an address, which is here. So let's go back to debugger. Let's hit Control-C just so we hit a break. And we're going to do vprot on that actual address. So we can see, of course, we successfully leaked it. It's a valid address. It's part of an anon mapping. And if we go back to the original that we were looking at, which this was the original, right? The original value of the commands pointer. We overrode it with a null. It's a valid address. And so we found that the next byte was going to be EO. So which let me double check. Yes, EO right here. So that's valid. And then the next one is 3.2. And again, we can compare that to our actual POC here. So 3.2. Let's try 3.1, right? So 3.1. So 3.1, even though it's a valid address, we technically can't write to it, right? So that's why we got a crash. Now, if we would have been able to write to it, we would have gotten a response back. And since this is one of those vulnerabilities where, yes, we can write to an address, but technically speaking, if it doesn't have the write permission allowed, it's going to cause an exception, right? Now, something interesting to note here is that this does lie within libc, right? But that brings up another situation we're going to have to deal with. So even though we do have a valid leak, right? Here's the leak. We still don't know where libc is. And to actually do anything useful to, generate a wrap chain, if we're going to do that path, if we're going to call system, etc., whatever way we decide to take, we need to know the address of libc. So despite us having a leak, it's in an anon mapping. So we have to figure out how to leak libc at this point. So let's take a look at the next proof of concept. This was a section that took me quite a while, honestly. I would say just as long, if not longer, than getting the initial leak. Because at this point, again, I went on my own, I tried to figure it out. And I think you guys should definitely check out the other write-ups, because from my understanding, because once I got it, I went and checked how they did it, and they did it differently than me, right? But the way I did it was basically I got the leaked address, and I was looking from the starting address to this ending address. And basically these 3 bits, I would try to brute force my way to find every possible address between these ranges. From that list of valid addresses, right, places we can write to, I would use the check win function to see the gaps in between the previous leak from the current leak. And if it was larger than a page, which is about 0x 1000 bytes, then I could assume that I've entered a new memory region. Now, depending on the amount of times this was discovered on a consistent basis, I could then determine that that address was going to be a good candidate to use as a base address, which I could then offset to find the address of libc. And so let's take a look at that check win function. So here, like I said, basically we're making sure that the distance is larger than a page. And if so, we document that. And then we iterate over each of the addresses. And if the gap is that of a consistent gap, which I've noticed to then be able to be used to get an offset of libc, then, of course, I give it that offset based on the gap size, and I have the address of libc. Hopefully that made sense. I know it's a lot, but I actually wrote a program to be able to find this. So I called it pattern search. So I won't go over the code just because it's madness. There's just the first line, okay? But basically, the way that this program works is it's going to take all of the leaked addresses that we're able to find from those ranges, right? From the leaked to the last 3 bits, or the upper 3 bits, whatever you want to call it, being changed to FFF. And then it's going to look for any similarities or any differences. That's what this program does. I had a bunch of different functions to test different things, but ultimately what I found was that gap was a consistent variable that allowed me to be able to deterministically find an address that I can use as a base to then offset into libc. Again, hopefully that made sense. So if we run it, we can see exactly what I'm talking about, right? So 4109 here, 4109, 4109. So that address was found every time to contain a distance of 0x 20C000, right? Because I kept finding it, that's a reliable gap. And so these gaps here are another example of reliable gaps. And this was after 3 different runs that I was able to determine this. Again, to be able to do this, you're going to have to write a program to do that similar operation. But that's what I did to be able to leak libc. Again, hopefully that made sense. I highly encourage you to really try to figure this out, because it feels good when you get it. Trust me. Like, the journey there sucks. All right. This isn't one of those memes where it's like, it's not about the destination, it's about the journey. No, okay, the journey sucks. I'm going to be honest. The journey sucks. But when you get to the destination, then you can pretend like the journey rocked. You know, you know what I mean? But in reality, it was rocky. All right. But anyway, let's go ahead and run it. So Python 3, POC 4, and then challenge, and then 5566. And if we go back, let's go ahead, run it here. I'm not going to attach yet, but I'm going to get it ready. And let's run it. Nice. So the exploit finished, and you can see that we did find that gap that we were looking for. And we, theoretically, right, at this point, we've successfully leaked libc. So I'm going to copy this, and I'm going to go back, and this time I am going to attach. And let's run a vmap, open another session down here, and we're going to compare our leaked libc, which is here, to the libc of the program, which is here. So if we do libc equals to leaked libc, we can see that we have successfully leaked libc from the target application. So at this point, now we're ready to weaponize the exploit, or not weaponize, but write a working proof of concept / exploit where we're able to get a shell, right? All right, so let's go ahead and bring up the next proof of concept. So it's going to be POC 5. And here, basically what I ended up doing is I ended up using this technique where we overwrite the RTLD global .dl underscore RTLD lock recursive function along with the contents of what RTLD underscore global dot underscore DL underscore DL lock points to. Mouthful, I know. Basically, we're overriding this with a function pointer of system, and we're leaving this the same because that's how it's going to be invoked. It's something that gets invoked passively. What do I mean by that? That means that once we've committed the overwrite, it's not going to trigger right away. We kind of have to wait for it to execute. And the reason why is because this works with the dynamic loader. So essentially, whenever it triggers an exception or a thread is created, etc., right? Certain events have to occur in order for this to happen. At least that's my understanding of it. I could be wrong, but that's basically how it works. And I actually got this technique from this blog post from the NCC group in which they exploit CVE-2018-1160. And funny enough, this is actually the same protocol. This is AFPD. This is just a newer vulnerability per se, and this is them showing the technique, and they go into more detail than I do. So I would recommend you check out their blog post, and I will keep a link in the description below. So let's go ahead and run this. So I have the listener set up and I have the POC ready to run, but I do want to note, I launched the server and then I logged out. And this is important because you'll see if you run this, that basically you'll get the shell, but you'll almost have to wait until the user exits the session. And I think it's because of the way that the process is tied to the user when they launch the server, if that makes sense. But regardless, let's go ahead and let this run. All right, nice. So exploitation completed. And again, since this is something that's going to execute in the background passively, not right away, we're going to have to wait. So let's give it a couple minutes and we should see our shell pop up in the upper terminal up here. All right, so that took about 3 minutes. So what is that, like 200 seconds? Pretty brutal. But if we do an LSB release tac A, we can see that we are in fact inside the Ubuntu machine, and an ID, why not, even though of course we can see the full shell that we are running as the mean user. So at this point, we've successfully achieved code execution. Let me go ahead and exit this session and clear the screen here, reload up the listener, and let's actually see this happen, right? I'm going to go ahead and also pull up the source. So let me make this smaller here, actually. So Vim POC 5. Oh, I'm probably looking at it in the other window here. Oh, actually, yeah, this should be fine. So let's go here. Let's close this. Leave this as is. Let's log back into the challenge machine. Make sure we kill that process. If it's still running, that is. Doesn't look like it is. So we're gonna cd into the directory. We're gonna run the server again. And we're gonna go ahead and attach. And the reason we're gonna attach is because we wanna see the values that we're overriding using the exploit. So where is this for loop that I've been using? Because I do not know it by memory. Okay, there we go. Now we can go ahead and attach. And let's go ahead and get those values here. So this is the first one. This is the function pointer. So x/xg, and we're going to do an ampersand since we want the address of this function. Okay, so here it is. Let's go ahead and take some notes and save it. And next, we're going to go ahead and get the actual parameter we're going to be overriding, or rather the contents of what it points to. So x/xg ampersand, and that's what we're going to be overriding. So let's go ahead and continue and launch the exploit again. And of course we have to continue. It's going to go ahead and exit, which is fine. And we'll be attaching once it's done. So let's go ahead and let that run. So we're going to go ahead and cancel it actually just because it's having issues. And oh, looks like the session completely died. So go ahead and do pkill SSH. See if I can even SSH into the challenge environment. All right, so I'm not sure what exactly happened, but it looks like the actual target environment crashed. Let me go ahead and reboot it. So I actually ended up needing to reboot my Kali machine, but I went ahead and got started. I attached the debugger, and of course I've launched a process. Now, going back to source code, I actually need it because I don't have this function memorized. I doubt anyone does, but then again, there's always someone. So we're going to go ahead and get that information. So go back to debugger, x/xg, ampersand, because of course this is a function pointer. So we're going to get that there. And then we're going to do the same thing with the actual argument that's being passed. And actually, this is the one where the ampersand matters more. So do that here. Open another terminal, put this to the side. I'm basically just going to save this information so that I don't have to remember it, because whenever the memory corruption occurs, we're probably not going to be able to dynamically resolve it the way we're doing it now. So let's go ahead and let it continue. Actually, let me delete the breakpoint that we created, which we're still using the same script. So that's the breakpoint that I just deleted. Let this run, close this since we're not using it anymore. Let's go ahead and actually have a handler up just in case. But in reality, we really don't have to worry about it. So let's go ahead and let this run. Then I'll come back to it once we see that we have, in fact, corrupted the values that we're expecting to corrupt, right? All right, so it failed to find libc. So we're basically just going to do the same thing again. We're going to launch it, and I'm going to kill it first. I love how I can just type this out, but of course, it's just ingrained in all of us to do the up arrow, right? But launch it, attach. Actually, I'm not going to have a listener up. Maybe that'll make it smoother. I feel like I'm using so many resources at this point that that might be what it is too. So let's get the actual function pointer. Let's get the variable or argument. All right. Just clearing the notes on the other side just so it doesn't confuse me. Then let's detach. And then let's run it. All right, now we wait. And hopefully libc this time, because the finickiness of exploits, man. All right, so at this point, the exploit should have went ahead and overwritten the values that we're expected to overwrite, that being the address and of course the contents of which a pointer is pointing to, or an address. So let's go ahead and do the loop. Attach once again. And you'll notice if we try to do it like this, we will get missing elf symbol. This is just because of the memory corruption. So that's why we went ahead and saved those values before. And if we do an x/xg on that address, we can see now that it points to the system function. And we can verify this doing x/xg __ libc system. And of course, we can see that they are equal. And now we can also go ahead and check the actual DL load lock, right? So x/xg DL load lock, and we can see that it now points to our actual payload string. That means that, of course, that when this is invoked, just as you saw before, we will have successful exploitation and we'll capture our reverse shell. So at this point, we can pretty much, celebrate because we've got our shell and we successfully exploited CVE-1160. All right, guys, so I have absolutely terrible news. We're not done yet. So the libc that the target actually uses is completely different than what we've been developing our exploit for. Now, I was going to include how to overcome this in this video, but I think in the spirit of the challenge, right? I'm going to let you guys figure that out yourself. Don't hate me. All right. In fact, I might still have the output out from me running it over here. Yeah, let me clear this. We'll run it again together. But basically, I know for a fact, based on the output of the exploit, you guys can figure it out with that alone. Okay, so I'm not leaving you completely in the dark, and I'm going to show you how you can build the environment. So in this Netatalk Docker directory, I have the config file, the binary, the libc provided to us by pwnable. I've created a flag, and of course we have Dockerfile. So if we look at Dockerfile, basically this was a ChatGPT generated Dockerfile. I basically told it, I told it what I needed, right? And I had it install pwnable, all the tools I do use whenever I'm debugging. Some of these I added myself, and then of course I created a working directory where everything's going to be housed. I copied the local contents to the Docker container, and this I believe is to force the loader to load this libc from the challenge path, where of course the AFPD binary is going to be running, and we're exposing port 5566. So to build this, we're going to run docker build tact netatalk. I did CVE, but let's just go ahead and call it doc. So let that build. It's done. And now we're going to go ahead and actually attach by doing docker run tac rm tac it, the ports we'd use, which I'm going to include 1, 2, 3, 4 since that's the debugging port. And for the name, I'm going to do netatalk doc and then bin bash. Oh, my bad. Let me do netatalk doc again. There we go. And so now if we go back to the challenge, we're ready to run it. Make sure I have a listener up actually. And what we're going to do is we're going to do AFPD tac d tac f afp.conf. Oh, do an ampersand so it runs in the background. And let's go ahead and let this run. Now, it's a lot faster, of course, since we're sending these packets to the local host. This one took trial and error, so if it doesn't work, yeah, see, like right now, it didn't work the first time, just rerun it. It may also be that this uses a lot of system resources since we're technically crashing it over and over and over again, so it kind of does dump files. And just be patient with it, I would say. If you theoretically know what it's supposed to be doing, you should be fine. Like you will get it, right? I think the Docker container is just trash, honestly, and this virtual machine in particular. I need to allocate more resources to it. And yeah, see, there you go. It found it. And now it's just going to, well, I won't say, but I know you, I have faith in you guys. I know you can figure it out. Okay. It'll be worth the effort. I promise. And if you still have trouble with this over a considerable amount of time, don't be afraid to ping me on Discord or any of the other platforms you guys message me on. I feel like you guys message me everywhere. So wherever you want, hit me up. And I don't mind helping. Now, if months after this video has released, you ask me for help, bear with me because I'm probably working on other exploits from that time period, from whenever I posted this and whenever you're asking me. So I may have to kind of refresh my brain to get in the position or mindset of this particular exploit. Anyway, gonna go ahead and let this run, and we should see the flag here in a minute, which I programmed the flag, of course. You can set it to whatever you want. I think I set it to high, but yeah, we'll see it here in a second. And there we go. We have successfully captured the flag from the Docker container. It's going to still try the other addresses just because of the way I programmed it, but this should be enough information for you to get the flag. I was having a little bit of trouble getting it myself. In fact, at the time of recording, I didn't get it. So if you guys are in that same boat, I may or may not try to capture it and see what's going on. I think it's really just the payload I'm using that hits the host to cat the flag. But honestly, if I'm not able to get it tonight, I'm just going to let it go, because ultimately, again, the goal with all of these challenges is to learn new techniques. I feel like I've achieved that. I'm happy with the results. And yeah, thank you guys for watching. I really appreciate the support. And as you know, I'm extremely passionate about malware and exploit development, and I wanted to push these videos out in a lot of the different things I release because of how difficult it actually is to break into this subcategory within cybersecurity because of how niche it is, and of course, all the different things you need to know to be able to even perform at a beginner level. That said, I'm happy to announce that I'm being sponsored by the Center for Cybersecurity Training, and they actually offer different courses that have impacted me directly in getting to where I am today, including Corland's Advanced Heap Exploitation course, in which directly afterwards, I was able to discover 3 different 0 days during my time at IBM. I've also taken other courses that they offer, such as Code Machine's malware techniques, which allowed me to develop things that unfortunately will never see the light of day due to NDA. But of course, those who have worked with me know the type of things that I have been capable of doing. And I do have to credit that to a lot of the different trainings that I've done. And one of them, of course, was offered through the Center for Cybersecurity Training. So if you're interested in this type of stuff, you want to learn more and you don't know where to get started, check out their courses through the link below, and I'll catch you next time.